All right, so I think this is the last topic for the day. Random variables. It's really something quite simple. We've already been dealing with them. A random variable is just something that describes an aspect of an individual in a population. So, for example, you could have a random variable called pink, and pink would just say, is this person pink or not? So for this person, they are not. So pink returns zero. Otherwise, it returns one. So the real it's not super important to understand this at kind of like the level that we're at, but mathematically, a random variable is actually a function. So it's like asking the question, pink. It's the question. It's not really the result. It's the question. So the when you put a particular person into that function, what it returns is a zero or a one, or you could have a random variable that is not discrete but is continuous, like age. So what is returned is this person's age. Um, and we say that the random variables, there's really nothing random about it, because it's just like describing a particular individual. The randomness comes from the fact that the answer depends on what person in the population you are asking about. For any particular person, the answer is fixed, right? Like I have a particular age. That's that number is fixed. It's known. It's not random. You have a particular age. Somebody has if somebody's wearing a hat or not, that's like a fixed quantity. There's no randomness really. The randomness comes in because when we're taking samples from a population, we don't actually know who we're gonna get in that population. So that's where the randomness comes in, is in the who we're actually getting data about and who we're not getting data about. So that's why these things are called random variables. But really, they're kind of not random if you think about if you had the whole population. There's nothing random about it. So you can define a lot of different kinds of random variables. Usually, you're taking multiple measurements of people in your sample. So you can imagine taking all those measurements for the people in the population. Ask what color and whether they're wearing a hat. Age, like I said, continuously valued random variables. And if you think about the kind of population data, where each person is a row of your data frame, and each column is something that describes that each person. The random variables are the columns. So for this person, we could have three random variables: age, whether or not they're pink, and whether or not they're wearing a hat. Those are the random variables. For another person, we can evaluate those same random variables to generate another row of data. So random variables are like the columns, and the individuals are the rows in your data frame. So hopefully that kind of helps think about what these things are. Of course, you can also define random variables for different kinds of populations. So we were talking about a population of samples, right? Each sample in that population can have some measurement associated with it. So, for example, we could define a random variable that just asks, are there any pink people in this sample at all? Or how many pink people are there in this sample? And so the value for this sample of any would be zero, and of count would be zero. For this one, count would be two, any would be one for this particular sample. So again, the answer is random because it depends on what sample you picked, or in the previously when we were looking at individuals, which individual you picked. But for any particular sample, the answer is really fixed. So the randomness just comes in when you're because you don't really know what sample you're going to get out of all the possible you could have gotten. A little bit of a notation. Usually we use these capital letters: X, Y, Z, W, U. Usually capital letters later in the alphabet are used to denote random variables. So in a data table like this, we would have like big X, big Y, big Z, would be denoting three different random variables. Like I said, technically they are functions. It's really a mapping between an individual and some kind of aspect. So for a particular individual, what is their age? The little omega, sometimes you will see it in like more advanced text that denotes what you can think of as an individual. Again, mathematically, it's abstracted away from individual or population or people. But you can basically think of that as like for this particular individual, for this like realization in they call outcome space. What is the value of this random variable there? So the main thing for you to take away is really just about the capital letters. If you see a capital letter, it's a random variable. It's a measurement about a particular person. All right, so let's do a couple more problems, and I think we call it. So let's. These are conceptual questions about random variables. If you do a survey of 100 New Zealanders and you ask about their height and whether they have diabetes, which of these are random variables? So the number of diabetics I get, the height of a particular person. If you don't know, Jacinda Ardern was the Prime Minister of New Zealand for many years. Any one of the height measurements I get, the average height among all New Zealanders. And for the things that you say are random, what are the relevant populations that induce the random? So let's do the third one first. I think this is the easiest. Any one of the height measurements I take, is that a random variable? Yeah. So for one of the measurements, since I'm surveying 100 people, I don't know who I'm going to get. So any one of those height measurements, basically like is like one of the numbers in a column like this. We'll have a column called height, and that any one of those measurements is random. I don't know what person necessarily a priori it comes from. So that should be considered a random variable, and it's random in the sense that I'm drawing from the broader population of New Zealanders. I don't know exactly which individual I'm going to get yet. So that's the population that induces the randomness. Now let's compare that to this one here, Jacinda Ardern's height. So this is a specific person who I know. I mean, she may not even appear in my sample, but since I already know who this person is, there's no randomness here, right? It's not like I'm drawing from some population and I could get this person or that person. Like I actually already know who this is, and I already know what her height is. So there's nothing random about this. This is actually just a fixed quantity. It is not a random variable. Now let's look at this one, the number of diabetics I get in my data set. This is really, we're going back to that example that we worked on just now, where we had lots of different samples that we were taking. Here, of course, we just have one sample, right? But we have to imagine, since the people in the population that I'm taking are random and I don't know who I'm going to get, I could get 10 diabetics, I could get 13, I could get 7, right? So that number is actually random. It's not a measurement about any individual in my population, right? It's a measurement about the sample as a whole. And so if I'm thinking about the probability of getting that, it's I have to think about the population of all the possible samples that I could have gotten. That's the relevant population. That population of all the possible samples is kind of induced by the population of people, by all the different like sets of people that I could have drawn from that. But to understand the idea, you just have to know that there is some population of samples, and you just get one of those, and you have a measurement about that sample. That's I think the easiest way to think about it. So that is a random variable, the number of diabetics in the sample. And then in contrast to that, we have the average height among all New Zealanders. Is that a random variable? No. Because again, there's actually no randomness. You have the entire population. It's all New Zealanders. You're taking the average height among all New Zealanders. If we took the average height in the sample, that would be exactly like this first one, the number of diabetics. It would just be like the average height in the sample. That's random. But the average height in the population is not random. I already have everyone. So there's no sampling. This is kind of equivalent in the world of like a population of samples to this, where like I know exactly who's in it, and I'm just taking the average in a fixed group of people. No randomness whatsoever. So hopefully that's helped in understanding, population, sample, what's random, what's not random, and a little bit of terminology, random variable, probability. So that when we talk about the probability of a random variable taking a specific value. So for example, the probability that hat is 1. All we're doing is counting up the number of rows. We've already seen this. We were doing this in R already. We're just counting up the number of rows, essentially, in the population data set where this occurs, or equivalent in the population, how many individuals have this. For how many individuals this hat returned the value 1. In terms of notation, again, we're not really going to see this much in this course. I'm just showing you because this is really... I think this notation actually helps understand a little bit. When you see this notation over here, probability that x, random variable x takes the value little x, right? So equivalent like hat equals 1. So little x is a fixed number, like 1 or 0 or 25. Big X is the random variable that it's a measurement, right? So a measurement that is taken on a particular person, and that person is random. So when you ask about the probability that a random variable takes a particular value, really what you're asking is the thing on the left. So the thing on the right is just a shorthand. It's a way of abbreviating the thing on the left. And what does this mean? This notation says probability of, so here we're this is interpreted as a count. So it's how many people, so little omega, remember, you can think of as like an individual. How many people are there such that this measurement taken on each person gives this value? So this is like how many, if X is whether or not they're wearing a hat. So I ask for each person in the population, are they wearing a hat? And if that value is 1, then I count them. If not, I don't. And all this is saying is count the proportion of people who are wearing a hat. And this is just a shorthand for that, effectively. So this becomes a little bit more meaningful or interesting or relevant when you're talking about continuous random variables, where there's like a lot of different possible values that they could take. But basically, I'm just trying to give you an idea of like what is the meaning of this notation. This thing you'll probably not see again unless you're kind of working with a more advanced textbook. You'll often see this used directly, but this is really just a shorthand for counting things. Similarly, if you want to ask about the probability that something is less than a particular value, so again, little x is used to indicate some fixed number, 5, 10, 23, whatever. Big X is the random variable. Again, this is just asking, like for example, if you were saying probability that the random variable age is less than 22. What does that mean? I'm just asking, in my population, how many people are younger than 22? Which is what this thing on the left to get at. So I'm just saying the thing on the right is defined as the thing on the left. The thing on the left is just counting in the population. Sorry, and when I say counting, I mean proportion, so relative to the total. Okay, so let's get our hands a little dirty with this. Let's use the New Zealand population data to compute these probabilities. So now we're working with a couple of continuous variables instead of just discrete. What's the probability that somebody is older than 65? What's the probability that somebody is younger than 30, given that they're diabetic? What's the probability that somebody is between 20 and 40, given that they're diabetic? So think about, what do these, before you even code anything, just think about, what do these symbols mean? Like, what is it that you're trying to count, right? And what subpopulation are you trying to count? And then think about how you're going to write code to count the thing that you want to count. So please try that for yourself. So first one is what? The x. So x is age. So all we have to do is count how many people are older than 65. Let's do it. So about 15% are older than 65. The next one we were asked about is how many younger than 30 given that they're diabetic. So remember, usually this is read as given. I think it's more helpful. I think I made a mistake actually. When I was reading this out, I said this was given, but it's actually and. But anyways, so this is, we'll talk about that in a sec. The conditioning is often read as given something is true. You can read it like that. I mean, that's fair. But I think it's more helpful to think among or like within the indicated subpopulation, because then you realize this is just a normal probability. It's just after you've already filtered down to a particular subpopulation. So let's do that one. So this is among diabetics. How many are less than 30? So first, we just need to get the diabetics. Diabetes. So among diabetics. And now we need to take this count. But now we're not asking about in relation to the total population. We need to ask them in relation to the total number of people with diabetes. And so maybe for this one, it's a little bit easy to break it up. Okay, so about 50%. And now this last one is the comma is like again a shorthand. People got tired of always writing and here, something like that. So the comma is you should when you see a comma, interpret it as an and or an intersection. So this is the joint probability that somebody is between 20 and 40 and they're also diabetic. Why is it like that? Was there any special meaning? What? No, it's just notation. It's just somebody started writing it that way. Everyone's like, sure, why not? Now we write it that way. So it's just something you have to know. There's nothing special. Okay, so let's go back to total population. So now we'll just count how many people match both of those conditions at the same time. So age between 20 and 40. A common mistake is you do this. This doesn't work in R because it evaluates this to be either true or false for each person in your data set. So you have to imagine there's like the age column is some continuous value, right? And it says, is that greater than 20? Yes or no? So the result of, if you kind of like imagine that it's doing this first, which it is, it's like you put parentheses around that, and the result of that expression is going to be a column of zeros and ones, or trues and falses. And then you're asking which of those trues and falses is less than 40. So that's not really what you want. And in fact, RC then says, I don't think that's what you want. And it says this is in fact a syntax error. So that's why this syntax doesn't work. What you actually need to do is say age is greater than 20, and at the same time, age has to be less than 40. So that's how you write this. And then there's one more condition that we also need to check, which is that they are diabetic. This one. Okay, that's it. And now what do? We just count how many rows we have. We compare that to the total number of rows in the total population. There we go. So about 1.5%. 1.5% of people satisfy both of these conditions. So hopefully that was straightforward. It's really the same thing that we are already doing, calculating probabilities, conditional probabilities. Given population data, we're just counting. The only difference here is that now we are working with some continuous random variables, where usually the probabilities that we're asking about are something being less than a particular value or greater than, rather than it's just something equals to 1 or not, true or false. But it's all the same idea. So I already talked about the comma meaning intersection or and, same thing. Um, I just wanted to point out that when a probability relationship holds generically, kind of no matter what the values are, that it's often written without it. So, for example, down here, um, this is really what we proved previously. That, for example, when x is less than 1, if you count up the total number of times in the subpopulation where y is less than 2, where x is less than 1, we know that we can write that as this joint probability divided by this marginal probability. This thing down here is just counting, right? It's just counting the particular condition where x is less than 1 and the particular condition where y is less than 2. But this kind of relationship holds even if I don't say x is less than 1, if I say x is equal to 3, if I say x is greater than -2, or y is equal to a billion. It doesn't matter what the numbers we put in there. It will be true for any events that we can choose. That those counts will be equal in that same way, and we get to the same rule. And so when we write this relationship in general, we just omit often those particular events, and we just say the probability of x given y is equal to the probability of x and y over the probability of y. Now, these things kind of don't make sense, right? Because what do I mean probability of y? This is like if y represents age, this is just like saying the probability of age. Makes no sense. Like, there's no probability of age. There's a probability that somebody's age is 23. There's a probability that somebody's age is greater than 5. That somebody's age is less than 20. Those are valid probabilities. There's no probability of just age, without referring to a value. But when we write that, implicitly what we mean is y equals little y, right? And wherever you see a big Y, like here, and here, you would write equals to little y. And whatever that little y is, it's the same in all of them. Or y is less than little y, and that's the same in all of them. And same for the x equals little x. So when we write it without those specific concrete values, we just kind of mean that this relationship is true no matter what those things are. So that can sometimes be a source of confusion, because again, here, this doesn't make sense if you're just talking about like what's the probability of diabetes in the population of age. It's like, no, in the population of people where age is something, right? So hopefully that helps demystify this notation a little bit. It's just a lazy shorthand, right? We just don't want to write equals x equals x. The thing about notation is that there's always a tension between writing stuff in a shorthand that's easy to read, and you don't have to like visually parse a lot of bullshit. Like if I wrote equal to little x everywhere and equal to little y everywhere, that'd be a lot of just symbols on the page, and it actually wouldn't really convey the meaning, because you have to parse through all that stuff before you actually see the main thesis, or like the big picture of what's trying to be conveyed, which is this kind of factorization that, or in this case, that this conditional probability is the ratio of a joint and a marginal probability. That's the main idea. So when you're trying to convey an idea, you often suppress unnecessary detail. That happens in any kind of argument that you make. If you're just talking to people, right, you're not going to get into all the historical detail of this, that, and the other. If you're just trying to make a point about who you should vote for or whatever, you'll save that for later, put it in an appendix, right? Same thing in mathematical notation. A lot of the time you write stuff in a way that's actually more terse than is really sufficient to fully explain the idea, because you're trying to get at what is the big picture, what's the main thing I'm trying to communicate here, and the details are kind of silently understood by context. So is that annoying for beginners? Yeah, it definitely is, but it's also a kind of a necessary tension. All right, so here I'm just going back to our using the notation like this. I'm giving you another example of this. I'm going back to the rule of the total probability rule that we looked at earlier, where if we're asking about what's the probability that somebody's wearing a hat, and what we know is the conditional probabilities of wearing a hat in each of these subpopulations, and also the probability of being in each of these subpopulations, we can write this total probability as a sum of these products. I'm just showing you how you would write that using this kind of probability notation. I'm also introducing. So that's the end. Yeah. Also introducing one extra thing here, which hopefully you've seen before, but maybe rusty on, which is this summation. So here, what we're saying is the probability of y. Again, that doesn't make sense. Really, this should be y equal to 1, or y equal to 5, or y greater than 5, whatever that is, right? So the probability of whatever that thing happening is equal to the probability that that happens in this subpopulation times the chance of being in that subpopulation, and then you're summing over the different subpopulations. So here, big X would represents, in this example, like color. So color can have values pink, gray, or black. So the little x here are those specific values. So this little thing just means sum. It's actually a Greek, in case you don't already know this, it's the Greek letter sigma, capital sigma, which is the letter S. So that's why it's a sum, sigma, sum. Okay. So we're adding up this term and this term and this term. We just write the generic version, and then we say all that we're changing from here to here to here is what the little value of x is. In other words, the color. So in the first iteration, we have pink, and then we add the same thing, but now we change the pink to gray, and then we add the same thing, but now we change the gray to black. So in terms of mathematical notation, we'd say that that specific value that this random variable is taking, that's what we're changing. And then we're adding up over all those values. So this is just really a shorter way of writing this total probability. And again, when you see this, this can be kind of intimidating or inscrutable. But this is all it is. It's just a shorter way of writing this kind of relationship. Okay. Also, something that's implicit here that I didn't write is that technically you should say that this, what is it that, you can also think of this as like a loop if you're familiar with programming. What is it that you're looping over? So here I just wrote loop over values of x, and it's unspecified here because, you know, I've written it generically. I'm again kind of leaving out the detail. But in this example, if, for example, x were a variable that took values pink, gray, and black, I would have to say, you know, kind of loop over the values pink, gray, and black. Right, so that I would know that this sum actually represents a sum over 3 terms. So sometimes you might see it written like that. Or x might be coded, these might be coded like as 1, 2, and 3. And then you'd kind of say like x equals 1, 2, 2, 3, or something like that. Anyways, it's just notation. There's a lot of different ways you can write it. What's important is being able to see the notation and relate it back to the main idea. All right. So that's it for this lecture on probability. Hopefully you got the main idea right. It's just counting in a population, but in reality, what we have are samples. We're gonna stick with populations, talking about populations for some time, so that we understand what are the kinds of questions that we're actually interested in asking, and what are the kinds of assumptions that we need to have in order to use samples to get at those things. Then we're finally going to get back a little bit to samples and analyzing data that we actually might collect. But you know, you got to walk before you run. So that's why we're doing this. Hope you found that interesting, and I'll see you next week.